topic is improper integration. Now before we start improper integration, we should have knowledge about finite, infinite intervals, bounded function, and of course the proper integration. So first, what is interval? Interval is a set of real numbers lying between two fixed endpoints with no gap. I mean, if we start from a point and end at a point, then there will be no gap in between the numbers. Like if I draw a straight line and take it as a real number line, so if this is 0 and this portion is negative and this is positive. Now if I take this point as -1 and this is as 1, then the interval -1 to 1 is actually representing the all real numbers lying in between -1 to 1. There will be no gap. According to the length of the interval, we can classify the intervals in two parts, like finite interval and infinite intervals. Now what is finite interval? When the length of the interval is finite, then it is finite interval, and if the length of the interval is infinite, then it is infinite interval. So if we write -infinity to 1, so this is representing an infinite interval. Why? Because the length is infinite. How to measure the length? This is infinite. Now how to measure the length? Like if a comma b is an interval, then length is equal to b minus a. This is the length. So for infinity, the length is infinity, so the interval is infinite interval. And if we take like -1 to 1, this is an example of finite interval. Now there is another thing, like I am writing 4 types of intervals. Let's say a and b are finite number. Okay, so all these intervals, these 4 intervals are finite intervals. But look at the first interval. The first interval is representation of closed interval. Why this is closed? Because if we write third bracket instead of first bracket, then it indicates the interval is starting from that point, which means this first set, it has a and b as element. Now look at the second interval. The second interval closed from the left side but open on the right side. So in this particular interval there is a, but b is not included. Likewise, in third interval, a is not included but b is included, and the fourth interval, a and b both are not included. So in this fourth interval there are numbers in between a to b but excluding a to b. This is open interval. So we already know about intervals. I am just repeating this to as a recap. Now what is bounded function? Now bounded function. Now what is bounded function? A function is said to be bounded function if its range is bounded. Range bounded means there will be particular numbers for which all the values of the function will be lie in between. Like if we write bounded function, f is bounded. Let f be a function from closed interval ab to r. R is real number, set of real numbers. So there should be capital M, or obviously small m is less or equal capital M, such that M less or equal fx less or equal capital M for all x belongs to AB. So this is actually indicating the values of the function will be lie in between two numbers, or if we take mod, then just we can write mod of fx less or equal to k for some real k, for some real number k, obviously for all x belongs to closed interval AB. So this is the definition of bounded function. Now we already know what is proper integral. Proper integral means the usual integration that we already know about. So proper integration suppose integration a to b fx dx is a proper integration, then if it is a proper integration, then two properties should be maintained. The first is the interval is finite or bounded, you can say. So first is AB is finite, and second is the integrand, I mean the function f, it should be bounded on that interval. So second is f is bounded on AB. If these two properties satisfy, then we can say the integration a to b fx dx is a proper integration. What about improper integration? So we can see that in proper integration there are two properties. First is the boundary, I mean the limit of the integration should be finite, as well as the function should be bounded. So what if the limit of the integration is not finite or the function is not bounded? So there are mostly three categories. Like one can be the first property is not satisfying, like the interval is not finite, right? This can happen, only the interval is not finite, but the function is bounded on that interval. So there is one possibility. There is another possibility, the interval is finite, but the function on that interval is not bounded. So another possibility. And the third possibility, both the criteria are not satisfying, like the interval is not finite as well as the function is not bounded on that interval. So based on this, we can get three types of improper integral. Now start with the first kind, improper integration solving. I am writing a general formula first, like integration a to infinity fx dx. Now this is an improper integration because the interval is not finite, it is infinite interval. Now let the function fx is bounded function. Let fx is bounded on a to infinity. The function is bounded function. So this is of first kind improper integration. Now we can write it as limit t tends to infinity integration a to t fx dx. Think infinity as a number. So infinity will be very large number. Now I am taking just one number in place of infinity. So I am taking t. Okay. Now this integration a to t fx dx is now a proper integration. So we can calculate the integral, right? But here the t is a variable, right? T is a very large number which we have taken instead of infinity. So just put the limit as t tends to infinity. So now we can calculate the integration easily, because now this integration part is a proper integration part, and next we just have to calculate the limit, which is very easy. T greater than a, because the upper limit should be greater. When this improper integration is said to be convergent, it is convergent if the limit exists finitely, and the integral is divergent if the limit is infinity or plus infinity or minus infinity. And if the integral is neither convergent nor divergent, then it is said to be oscillatory. So integration a to infinity fx dx is convergent if limit t tends to infinity integration a to t fx dx is finite, or we can write finitely exist. Divergent if this limit t tends to infinity integration a to t fx dx is equal to plus or minus infinity, and oscillating if this limit neither convergent nor divergent. Okay. Now similarly for if the interval is like integration minus infinity to b fx dx, then we can write this as limit t tends to minus infinity integration t to b fx dx, and for this t less than p. Okay. Now if the interval is from minus infinity to infinity, then we can break the interval into two parts, like if minus infinity to infinity fx dx, then this is like integration minus infinity to, let's say, c fx dx plus integration c to infinity fx dx, where c is any real number, c is any real number. We know how to calculate this part by the above formula, and from the first formula we also know how to calculate c to infinity fx dx. By calculating both the integrals, we can get the integration integral of minus infinity to infinity of a function. Now it's time to give some examples, like first example, integration 0 to infinity e to the power minus 3x dx. Okay, so we can write this as limit t tends to infinity, integration 0 to t e to the power minus 3x dx. So obviously t is greater than 0. So now first calculate the integration part. Now it is a proper integration. What is the integral value of e to the power 3x? It is nothing but e to the power minus 3x by minus 3. Limit is 0 to t. So this is equal to limit t tends to infinity minus 1/3 e to the power minus 3t, and e to the power 0 is 1, so this is minus 1. Now this minus 1/3 is constant part, so I am taking this first. This is limit t tends to infinity e to the power minus 3t minus 1. Now we have to calculate the limiting value. What is the value of limit t tends to infinity e to the power minus 3t? Basically e to the power 3t tends to infinity if t tends to infinity, right? Because exponential function, the nature of exponential function is if the power tends to infinity, then it goes to infinity also, because the value of p lie in between 2 to 3. So e to the power minus 3t obviously tends to 0 if t tends to infinity, right? If something goes to infinity, then the reciprocal of that will goes to 0. So this limiting part, this is actually 0. So this is 1/3 of 0 minus 1, which is equal to 1/3. So this limit gives the finite value, hence the integral is convergent integral and the value is 1/3. So it is convergent and the value is 1/3. Now take another example. Integration 2 to infinity 2x square by x to the power 4 minus 1 dx. is nothing but limit t tends to infinity integration 2 to t 2x square x to the power 4 minus 1 dx. Okay. Now we can write this function as x square plus 1 and x square minus 1, and x to the power 4 minus 1 is x square, like we can write this as x square minus 1 square. So this is a square minus b square formula, x square plus 1 and x square minus 1 dx. So this is limit t tends to infinity integration 2 to t 1 by x square minus 1 plus 1 by x square plus 1 dx. So this is t tends to infinity, and the integral value of 1 by x square minus 1, I mean the formula for 1 by x square minus a square, this is half of log x minus 1 x plus 1 plus, for x square plus 1 tan inverse x by a is 1, so this is just only tan inverse x. Limit is 2 to t. Now this is limit t tends to infinity half of log t minus 1 t plus 1 plus tan inverse t minus half of log 1/3 minus tan inverse 2. Now limit t tends to infinity, so I am writing the half first, half of limit t tends to infinity log of t minus 1 t plus 1 plus limit t tends to infinity tan inverse t minus, these are all constant term, so so limit is not applicable. Now we can write log 1 by 3 as minus of log 3, so this is minus minus plus half of log 3 minus tan inverse 2. Now this is equal to half of limit t tends to infinity log 1 minus 1 by t 1 plus 1 by t plus, for tan pi by 2 tan goes to infinity, so limit t tends to infinity tan inverse t is pi by 2 plus half of log 3 minus tan inverse 2. So this is equal to half of, now if we put the limiting value, if t tends to infinity, we know that if t tends to infinity, then 1 by t tends to 0. So this is log 1 minus 0 by 1 plus 0. So this is log 1 plus pi by 2 plus half of log 3 minus tan inverse 2. Now this part, this is equal to 0. So the ultimate result is pi by 2 plus half of log 3 minus tan inverse 2. This is the result. Now take another example, integration minus infinity to 0 e to the power minus x dx. So similarly, limit t tends to minus infinity, integration t to 0 e to the power minus x dx. This is limit t tends to minus infinity, integration is e to the power minus x by minus 1 t to 0. So this is limit t tends to minus infinity, e to the power 0 is 1, so this is minus 1 minus minus plus e to the power minus t. So this is minus 1 plus limit t tends to minus infinity e to the power minus t. Now what is the value of limit t tends to minus infinity to the power minus t? E is 2 to 3, right? So E is a number in between 2 and 3. Now this limit e to the power minus t, t tends to minus infinity is equivalent to limit t tends to infinity to the power t, because we are taking like t is equal to minus t, then the limit should be minus infinity to infinity. So this is equivalent to this. When we put the power tends to infinity, I mean a very large number, then the whole number will be tends to infinity. So this is actually tending to infinity. So this value is tending to infinity. So here is the example of improper integral which is not convergent. Okay. Hence this integral is not convergent, or we can say divergent. Now how to solve second kind improper integration, like a b fx dx. So this is a second kind improper integration. So clearly fx is not bounded on AB. Now there are three parts. One, if the function is not bounded on its lower limit, like if it is not bounded at a. Another, if it is not bounded at b. And the last one is if it is not bounded at a point which is in between a and b. So first start with if it is not bounded at a. So let first fx is not bounded at x equal to a, only at x equal to a. Okay. Then we can write this as a to b fx dx equal to limit epsilon tends to 0 plus integration a plus epsilon to b fx dx. Now the integral is integration a plus epsilon to b fx dx. The function was bounded except x equal to a. So now in this interval, when the interval is a plus epsilon to b, now this interval a is excluded, right? Epsilon is always a very small number, that is why we are taking the limit as epsilon tends to 0 plus. Like if this is the interval, this is a and this is b. Now the function is not bounded at this point a. So we can take the value just after a, like if we take the interval from here, then there is no problem, because on that interval now the function is bounded, so we can calculate it as a proper integral. So we only shift the limiting value for which the function is not bounded very slightly. 1 plus epsilon is very near value but greater value of a. So epsilon tends to 0 means epsilon is very close to 0 in positive sense, very close to 0, I mean greater than 0 but very close to 0. So a plus epsilon is very close to a but slightly greater than a, just because f was not bounded at the interval a to b, we are shifting the interval slightly, so that now in that interval the function is bounded. Now the interval is a plus epsilon to b, so on that interval fx is bounded, so we can calculate the integral and we just have to take the limiting value. Now if fx is not bounded at x equal to b, then integral a to b fx dx is equal to limit epsilon tends to 0 plus integration a to b minus epsilon fx dx. Now the scenario is same, but why b minus epsilon? Because now the interval, actually the interval was a to b, in which the function was not bounded at b, the upper limit b. So we have to shift the interval slightly in which the function is bounded on that interval, right? Now if we take b plus epsilon, that means the b point is then also in the interval, so the function would be not bounded on that interval. So our aim is to avoid the point b, so we are taking a very close number to b but smaller than b, that is why b minus epsilon. And now in this interval the function is bounded, and by taking the limiting value we can calculate the integral. Now what if the function is not bounded at a point C, where C is in between A to B? Then we can write it as A to C fx dx plus C to B fx dx, and we can take the limit like integration a to c minus epsilon fx dx plus integration c plus epsilon to b fx dx. And do you know how to calculate thereafter? Now I am taking an example of second kind improper integration. So we know the rule. First check at which point the function is not bounded. So the function is 1 by square root 4 minus x square. So clearly the function is not bounded at x equal to 2, because at x equal to 2 the denominator is 0, the function will be not bounded. But at x equal to 0 there is no problem, the function is bounded function. So here the upper limit is not bounded. So I am taking limit epsilon tends to 0 plus integration from 0 to 2 minus epsilon dx square root 4 minus x square. So this is equal to limit epsilon tends to 0 plus, and now the integral value, this is sine inverse x by a, where a is 2, because 2 square minus x square this is. So this is 0 to 2 minus epsilon equal to limit epsilon tends to 0 plus sine inverse 2 minus epsilon by 2 minus sine inverse 0. Now sine inverse 0 is 0, so this is nothing but 0 epsilon tends to 0 plus sine inverse 2 minus epsilon by 2. Now when epsilon is tends to 0, this part is 0, so this is sine inverse 2 by 2 which is sine inverse 1. So this is sine inverse 1. Now value of sine inverse 1 is pi by 2. So this is giving the finite value, hence we can say this improper integral is convergent and converges to pi by 2. So this is convergent and converges to pi by 2. Now take another example, like integration minus 1 to 1 dx by x square. So we can see that here the function is 1 by x square, which is not bounded at x equal to 0, but 0 point is in between minus 1 to 1. So we have to write this as integration minus 1 to 0 dx by x square plus 0 to 1 dx by x square. Now taking the limiting value, limit epsilon tends to 0 plus limit minus 1 to 0 minus epsilon dx by x square plus limit epsilon tends to 0 plus integration 0 plus epsilon to 1 dx by x square. So this is equal to limit epsilon tends to 0 plus integration value is minus 1 by x, limiting value minus 1 to minus epsilon plus limit epsilon tends to 0 plus integration value minus 1 by x epsilon to 1. This is equal to limit epsilon tends to 0 plus 1 by epsilon minus 1. This is limit epsilon tends to 0 plus minus 1 plus 1 by epsilon. Now, if the denominator is tends to 0, then the whole value is tending to infinity. We know that, right? Like if x tends to 0, then 1 by x is tends to infinity and vice versa. So, if epsilon is tending to 0, then 1 by epsilon is tending to infinity. So, this is infinity minus 1 plus this is also minus 1 plus infinity. So, this is actually tending to infinity. So, this integral minus 1 to 1 dx by x square is divergent. And similarly, we can find whether the improper integration is convergent or divergent. So, these are the basics of finding improper integration. There are more properties and techniques to find improper integration. That's it for today. Thank you for watching.